Hello my dear students, welcome back to the St. Joseph Composite PU College, Vijaypur. I'm Rahul, chemistry faculty, and in this video I'm going to explain you that after adding a non-volatile solute to the water, the boiling point of water is increased. Not only water, any of the volatile solvent if you add a non-volatile solute in that solvent, the boiling point of that liquid get increased, and that is known as increase of boiling point or lower to higher of boiling point, or we can call it as elevation of boiling point. That what we have at the title here. You can see that elevation of boiling point. The simple question is that why after adding the non-volatile solute to a solvent and that solution having higher boiling point as compared to solvent. Let's understand this using a simple graph. The graph is here. This is a coordinate where I use here vapor pressure. Okay, now along this coordinate axis, I will take the temperature T. Now assume that somewhere here is 25 degrees Celsius or room temperature, somewhere here temperature is 25 degrees Celsius or room temperature. If I consider only the solvent, okay, the solvent I'm considering first. The solvent at the room temperature having vapor pressure somewhere here. This is the vapor pressure correspond to the at room temperature of the solvent. As I increase the temperature, the vapor pressure of that solvent also get increased, because after increasing the temperature or providing the heat content, the water molecules or the solvent molecules gain kinetic energy, and that kinetic energy allow the molecule to escape the surface, and by that the vapor pressure get increased because vaporization also get increased here. Like this, the vapor pressure is increased. So somewhere here, so this is 0, and here we have the vapor pressure that is equals to 1 atm, 1 atmospheric pressure. Okay, so let me take this 1 atmospheric pressure like this. That is okay. Let me draw a line here. This is a line that corresponds to 1 atmospheric pressure. The vapor pressure is exactly equal to 1 atmospheric pressure, and that temperature I have to take, that temperature will be like here. If I draw a line here, this will be the temperature of the solvent at which the vapor pressure of this solvent become exactly equal to 1 atm, and this temperature I'm going to refer here as T0B. That itself is a boiling point. So by this we can understand what is boiling point. The boiling point is a temperature at which the vapor pressure of the solvent become exactly equals to 1 atmospheric pressure. Why only 1 atmospheric pressure? Because on the earth we have 1 atmospheric pressure. If you go on in the different places, there is different atmospheric pressures are there. At the higher mountain, the vapor pressure is required less, because obviously there is a less atmospheric pressure is there. We'll discuss it later. But thing is that, so this is the boiling point, students. Okay. Now what I do that to the same solvent, I'm going to add some non-volatile solute like sodium chloride. Okay, and that becomes the solution of non-volatile solute. For example, you can take water and table salt, that's sodium chloride, that forms your you can say that in generally that is a solution which contains non-volatile solute. And due to what happens there, usually what we know that when you add a non-volatile solute to the volatile solvent, the surface of the solvent get occupied by the some of the solute particles. As I mentioned in the previous videos, you go and check that. So surface area is decreased, the number of molecules of the solvent at the surface also decreases, and vaporization is also decreased, and by that the vapor pressure is also get decreased. Okay, so it means that the vapor pressure of solution which contain non-volatile solute is lower than that of the solvent, right? Because the number of the vapor molecules present above the surface of the container or the liquid is less. Okay, so therefore at exact the 25 degrees Celsius, the vapor pressure of the solution somewhere here, that is less, that is somewhat less it is. Now if you go on increasing the temperature, the vapor pressure of the solution get increased. So the increase you can represent like this. So this is how the vapor pressure of the solution is increased. So somewhere here we reached 1 atmospheric pressure. Now let me extend this once again. So what I get here, so here is the line. This is a 1 atmospheric pressure we have. We're going to draw the line here, and corresponding temperature will be here. So this is corresponding temperature, and this temperature we're going to term it as the TB. TB is the temperature at which the solution start boiling, or generally you can call it the boiling point of solution. There is a difference. T naught B is the boiling point of solvent and TB is the boiling point of solution. There is a difference. You can see that out of these two, TB is larger compared to T naught B. Okay, this indicates that always the boiling point of solvent, the boiling point of solvent is always greater than, sorry, it's always smaller than the boiling point of solutions. So those students who know or who knew the concept working behind this is the molecules present at the surface area. Okay, so in the solvent, you know that the solvent molecules are more at the number at the surface, but at the solution the number of solvent molecules is less because the surface area is less due to accumulation of some of the solute particles at the surface. Okay, this is a fact, students. Okay, so this is how the boiling point of the solution get changed when you add non-volatile solute to that. Okay, this is one part. Okay, let's move to some important terminologies here. The first thing, we're going to define what happens when you add a non-volatile solute to a solvent. Okay, the vapor pressure of the solution, vapor pressure of solution of non-volatile solute in volatile solvent is always lower than yes, this is important part, lower than pure solvent. Okay, why this is so? Number of solvent molecules at the surface area are different for solution as well as for solvent, and because of this reason, students, what happens here, the boiling point varies. Okay, so liquid always boils. This is a requirement for the boiling point. Liquid, okay, all the liquids always boils at that temperature where vapor pressure of liquid become exactly equals to atmospheric pressure. This is the base of the concept, students. So anything that liquid is boiling at particular temperature means at that boiling point the vapor pressure of any of the liquid become exactly equals to the atmospheric pressure. At that moment we can say that the liquid is boiling. Okay, now the fact is that the vaporization of the solution is less, and therefore you have to heat it more to make the vapor pressure become exactly equal to atmospheric pressure. And therefore I'm going to relate this with another statement. The other statement is, therefore the boiling point of pure solution, I don't want to write here, pure solution, boiling point of solution is always higher than the pure solvent. Student. Okay, this is the required statement, students. Okay, now as I drawn a graph here, so whatever the change is there, change in temperature, this part of discussion is very important. This change we can represent here delta TB, change in boiling point or increase in the boiling point, or you can call it as the elevation of boiling point. So that can be given here. So delta TB can be given here like delta TB is equal to, so TB is larger than T naught B, so therefore I'm going to write here TB minus T naught B. Already I mentioned that what is TB and T naught B in the graph. Okay, but experiments shows something very interesting. Experiment shows that so delta T naught B is there now, it is directly proportional to molality, that is we can represent here M, molality. So because the elevation of boiling point is a colligative property, students. The colligative properties are depends upon the number of solute particles present in the solution. If the more number of solute particles are there, then the property also gets changed. Such property is one, that is elevation of boiling point. that this statement indicate that delta TB, that is elevation of boiling point or increase in the boiling point, is directly proportional to concentration of the solute or concentration of solution, or you can say in general word the number of solute particles. So I want to remove the proportionality term here, that's the delta TB, that equals to, I will write the term here KB, that's the constant multiplied with the molality. Okay, now what is KB here? The KB is nothing but delta TB only, that is delta TB is equal to KB only when the molality is equal to 1. When the molality will be 1, the molality is 1 when a 1 mole of the non-volatile solute is added to a non-volatile solvent, that should be of 1 kg. Okay, so that is the definition. We can provide the definition for this. We can write the definition for the KB also. So what KB is called as? KB is called as elevation constant. It is called as elevation constant. Elevation constant. Okay, or it is called as molal elevation constant. Molal elevation constant. Okay, and after that even it is called as ebuloscopic constant or ebuloscopic constant. Ebuloscopic constant we have. Okay, these are the different terms you can get here. Now we'll define the KB. KB, that is molal elevation constant. Molal elevation constant. Elevation constant is nothing but a elevation of boiling point, right? This delta TB is elevation of boiling point. Delta is elevation of boiling point when 1 mole of non-volatile solute should be added, non-volatile solute added to 1 kg or 1000 grams of volatile solvent. Okay, volatile solvent it is. So this is the definition for the molal elevation constant or KB. This is the definition for the KB students. Okay, now let's go with one more term here. The molality can be given here as M is equal to number of moles of solute B. I will take solute B divided by mass of the solvent taken, that is WA I will use. That should be in the in kg. This is the definition, right? The number of moles of solute B added in the weight of 1 kg of solvent. Okay, but we know that NB can be given here as weight of the solute taken divided by the molecular mass of the solute, that is MB. Okay, WA, if it is given in the grams, so then WA we can write in grams. I will write in grams. In grams I can write in a different way, that is given weight, that is WA, and that should be divided by 1000 because it is in the kg. We have to convert into, okay, gram it is we have to convert into kg, and therefore M is equal to we're going to write here WB divided by MB and whole divided by WA whole divided by 1000. Okay, given the weight of the solvent is there, no, that should be in the kg. So therefore this equation I will take here equation number 2, and the above equation is there, no, this one. I will take this equation as equation number 1. I will combine these two equations, and by that what I get here, okay, let's go, that is delta TB is equal to KB into WB by MB. Okay, MB it is MB, and multiplied with the 1000 because the denominator of denominator becomes numerator, that's divided by WA here. Now MB is equal to what do you get here? You just cross multiply, or you can say interchange delta TB and MB. We'll get here KB WB into 1000. Okay, and that should be divided by delta TB and multiplied by WA. This is the equation. This is the one of the equation we use to calculate the molecular mass of the solute, student. Very important equation, you have to remember this, because in upcoming classes I'm going to solve some of the problems on this formula. Thank you for watching this, students.